Hi, everyone. My name's Will. Today, I'm going to be taking you through an introduction to Cypher, the graph query language. I'm an engineer on the developer relations team at Neo4j. My contact info is on the screen there, so feel free to reach out. Happy to answer questions if you have them after the broadcast today. So on the developer relations team, I work on a number of things, things like building integrations for other tools that work with Neo4j. Currently, I'm working on a GraphQL integration for Neo4j, but I also talk to a lot of users and help them be successful with graphs in Neo4j. So today we're going to be talking about Cypher, which is the graph query language. Here's a rough outline for the next 60 minutes or so. We're going to start with just a brief overview of Neo4j, just so that we're all on the same page. This will be pretty quick here because we want to spend a lot of time talking about Cypher specifically. So we'll do a little bit of an overview of Cypher, but then I'm a developer, so I like to focus on developer-facing aspects of Cypher. So we'll do a hands-on introduction to Cypher. We'll have an existing data set that we're going to work with, and we'll try to answer some interesting questions, building up our knowledge of Cypher as we go through that. We'll spend a little bit of time just pointing out some interesting resources for you to get more acquainted with Cypher and Neo4j, and then we'll leave plenty of time at the end, hopefully, to answer your questions. So if you have questions during this webinar, please feel free to submit them, and we'll try to answer those at the end. So with that, let's go ahead and get started. Let's talk a little bit about Neo4j. So I think the most concise way to explain something is in the form of a tweet. So here's Neo4j in 140 characters. Neo4j is open source software that stores and queries data as nodes and relationships using the Cypher query language with index-free adjacency. So there's a lot there. Let's unpack that a little bit. So first of all, Neo4j is open source software. The code is on GitHub. Anyone can download it. You can also use Docker. There's a Debian package for Neo4j. Lots of different ways to get started with Neo4j. You can even build it from source if you want to, but very much open source software that stores and queries data. So Neo4j is primarily a database. Transactional database, focused on durability. So when a transaction is acknowledged, that data is committed and durably saved to disk. Now, it also allows you to query your data for things like real-time operational workloads and also interesting graph analytics problems as well. It allows us to query our data as nodes and relationships. So Neo4j is a graph database. The graph piece is the data model. So the data model, the property graph data model, is composed of nodes. These are the entities in the graph and relationships that connect nodes. So on the right there, we can see an example data model. We have officer nodes that are connected to entity nodes that are connected to intermediary nodes, and then all of these are connected to address nodes by a registered address relationship. If you've seen this data model before, it comes from the Panama Papers dataset. So this was an investigative journalism project with some data from a Panamanian law firm that exposed many famous and infamous, we'll say, influential people throughout the world that had connections to offshore legal entities. And the team responsible for analyzing this data used Neo4j to make sense of these connections. And this is the data model that they used. You can actually download this data as a Neo4j database. It's also available on the Neo4j sandbox, which we'll talk a little bit about in a minute. Now, the next piece of our explanation here is that we're able to query our data as nodes and relationships using the Cypher query language. So we're talking a lot about Cypher today. Here's an example of a Cypher query. Now, this is a Cypher query for the data set that we just looked at, the Panama Papers data model. So you can see in that first line there, that's a match statement. So you can think of match as somewhat similar to maybe a select in SQL, where we're specifying, in this case, a graph pattern. So we're saying we want to find where this pattern exists in the graph and then return that to us. And we define a pattern by drawing these ASCII art sort of representations of our graph. So here we're looking for an address where the address property contains New York, so addresses in New York, that are connected to an officer node through this registered address relationship. Then we're looking for all entities, all legal entities connected to this officer. So this essentially says, show me all of the people with an address in New York and all of the offshore entities that they're connected to. And if we ran this query in Neo4j browser, so Neo4j browser, if you haven't used it before, is a query workbench and visualization tool for working with Neo4j. So it allows us to explore our graph data visually. So we would see this. This is just a small snapshot of all of the people with addresses in New York and the legal entities they're connected to. And we can sort of explore the graph by clicking on these nodes and moving them around. It's helpful to see where clusters emerge in the graph. But oftentimes, the answer to the question that we're trying to ask is not necessarily graph data. It could be tabular data, the result of an aggregation. So this query, this is just a slight modification of the previous query. This query essentially says, for all of the people with addresses in New York, what are the most popular jurisdictions of the legal entities that they're connected to? So again, we're defining the graph pattern that we're looking for, filtering for addresses that contain New York. But now in our return statement, you can see that we're calling an aggregation function, count. So we're counting the number of paths, in this case, grouped by jurisdiction. So in Cypher, anytime we return an aggregation along with something, we have an implicit group by of what we're returning it with. So in this case, we're grouping by jurisdiction, getting the count, and then ordering, looking at the top 10. So we can see that the most common jurisdiction for people with an address in New York to register legal entities from the Panama Papers data set is the British Virgin Islands, followed by the Cook Islands. So that's just an example where sometimes we're looking for tabular data, not just graph data or graph visualizations for answering our questions. Visualization can be an important component of working with graph data and graph databases, but oftentimes the answer to our question is the result of an aggregation. Okay, and the final important aspect that we're talking about in our simple explanation of Neo4j is that we're able to query our data as nodes and relationships using the Cypher query language with index-free adjacency. So index-free adjacency is an important performance characteristic of graph databases. Neo4j is a native graph database, which means that we actually store your data as a graph. We work with it as a graph the whole way through Neo4j. And that allows us to have an important performance characteristic called index-free adjacency. What this means is that in Neo4j, we can traverse from a node to any node that has a relationship, so any connected nodes. We can traverse that in constant time without having to do an index lookup operation. This is really, really important because it means that the performance characteristic of a traversal will be the same for a data set with 1 billion nodes as one with 1 million nodes. And this is really, really important because it means that our complex traversals that we're able to express with Cypher can scale to very, very large data sets. So that's Neo4j in 140 characters, open source software that stores and queries data as nodes and relationships using the Cypher query language with index-free adjacency. So now that we're all on the same page with Neo4j, and I think for some of you that was a bit of a review, let's talk about Cypher. So Cypher is a declarative query language for working with graphs and graph data for both reading and writing to the graph. It's very expressive, very intuitive, but still very powerful. And we'll see a few examples of why that is in a minute. But it's intended to be also very human readable and accessible not just for developers, but also I think for operations professionals or analysts. We see more and more non-developers using Neo4j browser to write Cypher queries to answer the questions that they're looking for. I think the Panama Papers example is a great example of where we can answer questions that are very, very specific, very, very complex, that we're able to express with Cypher that folks other than just developers are able to compose those queries. So let's dive into Cypher a little bit more. Now, when we say that Cypher is a declarative query language, what we mean is that we specify the data that we're interested in, not how to fetch that data from the database. And this is really important because it means that we just have to be able to define the data that we're looking for and not get bogged down in determining the actual database operations that we need to complete to fetch this data. Now, related to that is this concept of graph pattern matching. This is a big piece of what gives us the important expressiveness in Cypher. So nodes are defined within parentheses, relationships within brackets. That's the very basic graph pattern matching that we're talking about, where we define a graph pattern that we're looking for, and then it's up to Cypher to go find that in the graph. Now that's the basic components of the graph pattern using this simple ASCII art representation, but we can of course express more complex patterns. We can express key value pair properties within curly braces. We can do things like express variable length paths by using this variable length operator on our relationship. So we can, in this case, traverse up to 2 relationships deep rather than just a direct relationship. And there's a lot more in that pattern matching that we can use for expressing very, very powerful graph queries. So we said that Cypher is intended to be human readable. This helps with, I think, accessibility, but also it allows us to focus on our domain, focus on our data, not necessarily the database operations and more database specific things, right? So we just need to define the pattern we're looking for, either if it's querying data or also for data imports, define the pattern we want to create from data, iterate through a CSV file, things like that. So this is what makes Cypher very, very powerful, expressive, but also intuitive. Cypher is, of course, open source. Cypher is through the Open Cypher project. Cypher is an open standard for graph querying. So the Open Cypher project aims to provide information for implementing Cypher in different systems. So Cypher is not specific to Neo4j. There are a number of other graph databases and graph systems that have implemented Cypher as part of Open Cypher. There's a lot more information on opencypher.org that includes things like the grammar for Cypher and tools for building Cypher compliant integrations. Now, this is not specific to Cypher, but Neo4j uses a binary protocol called Bolt to speak Cypher to the database. So Bolt is an efficient binary protocol that allows for compressing data that's sent over the wire. There's a Bolt type system. Bolt data is encrypted by default. So there are a lot of benefits for using Bolt with Neo4j. There are many language drivers. Here are just a couple of examples: JavaScript, Java, .NET, Python. And these are idiomatic libraries. They're idiomatic to their language, but also provide a common interface for sending Cypher queries to Neo4j and working with the results. So if you're actually building an application that queries Neo4j, which is what most of us developers are doing, we want to make sure that we're using these Bolt language drivers. And they can also be used to build tighter integrations with other frameworks. So they're meant to be fairly low level. But for example, the Java driver has a OGM, an object graph mapper, that's built on top of the Bolt Java driver. And then there's a Spring Data integration that's built on top of that as well. So they really enable building integrations with your common frameworks. Here's an example of some code that is querying a Neo4j database. This example is Python, but this just gives you sort of an example of what using these Bolt drivers is like. In this case, we're importing the Neo4j driver library. We're instantiating a driver object by passing in the URL for Neo4j and also our credentials. Then we define a Cypher query. So in this case, we're looking for a specific user. In this case, we're passing in a name parameter. So we're looking for a specific user who's rated a movie, and we're returning all of the actors that have acted in movies that he's rated. We then create a session object. So a session is a lightweight object that we will just use for a defined amount of work. We'll create our session. We'll then execute the query, passing in the parameter. What we get back is a cursor of records, which we can then iterate through, in this case, just printing out the actor's name. Now, we're going to be using Neo4j Browser today. Neo4j Browser, like I said, is a query workbench for interacting with Neo4j and visualizing the results. Neo4j Browser, of course, uses the JavaScript Bolt driver under the hood for connecting to Neo4j. Great, so let's actually, now that we've had a chance to get a high-level look at some of the benefits of Cypher, let's actually use a graph dataset and do some hands-on querying of Neo4j with Cypher to build up our knowledge of Cypher a little bit. So let's talk a little bit about the data that we're going to use. If anyone's familiar with Yelp, Yelp is a business review site, I guess you could say. So every year they release what they call the Yelp Dataset Challenge, where they release some data from some select cities around the world. It includes information about businesses, users, the reviews of businesses. There's some social network data in there as well. And in the last webinar that I did, which was called Working with a Real World Dataset in Neo4j, we went through the process of modeling this Yelp data as a graph and then going through several different ways of importing this data into Neo4j. So what I'd like to do from here is pick up where we left off in that previous webinar. So if you remember that, great. We're going to pick up right where we left off and then start writing some Cypher queries to query this data. If you didn't catch that webinar, that's fine. We're going to talk a little bit about the data model that we're able to build, but we won't cover exactly how we imported that data. But don't worry, all of the code for importing that data is on GitHub at the link here as well. So let's talk about the graph data model. We'll talk about it in sort of abstract terms first, and then we'll talk about the specific graph data model that we're going to use to query in just a moment. So we said that the property graph model is composed of nodes. These are the entities in the graph, relationships, which have a direction, a single direction, connect nodes, and then we can store key value pair properties on our nodes. It's called the labeled property graph because each node can have one or more labels. Relationships have a single relationship type, but we can store an arbitrary number of key value pair properties on both the node and relationships. If you wanted to map these to language terminology, I find that helps sometimes. You can think of nodes as the nouns, relationships as the verbs, and then our properties would be adjectives that describe the nouns or adverbs that describe our relationships. So for this example, we started with this Yelp data set, which has 3 different JSON files for users, businesses, and then lots and lots of user reviews of businesses. So we have things like the user ID, their name. We have an array of their friends. That's this idea of some social network data. For the business, we have the business name, its categories, its address, latitude and longitude, lots of different attributes such as is it organic, the hours that it's open, this kind of thing. And then for every review, we know the user that wrote the review, the business ID that's being reviewed, and then we have text and the number of stars for the review. So in the previous webinar, we went through the process of converting from these JSON files into a graph data model. And just to refresh the data modeling process, the first thing that I like to do is identify the entities in the graph. And these become your nodes. Then think of what properties are relevant. So in this case, we have businesses, we have reviews, we have users, and we have category nodes. Now, category I chose to model explicitly as a node because if we model category as a node rather than as a property on the business, we're able to traverse through those category nodes to find similar businesses. So businesses that share a category, we can compute similarity metrics, so what businesses are most similar based on their overlapping categories. And this can help for things like real-time recommendations, if we need to recommend a restaurant that you might be interested in, things like that. Now, the next step is to identify relationships. So in this case, we have users that are friends with other users. Users wrote a review. The review is a review of a business, and a business is in a category. And the data modeling process for graph can be a little bit iterative. I think it often helps to go through this process, see if you can answer the questions that you have of the data. If not, iterate on the process to adjust your data model. There's nothing wrong with that. And in fact, graph is so flexible that it's very easy to evolve and refactor our data model once we get started. So this is the basic data model that we came up with. We loaded this into Neo4j. So we have this ready to go. And remember, there's a script on GitHub to import this data if you haven't done it already. But I think we can still, if you're not familiar with this data, I think we'll still learn a lot about Cypher along the way here. So let's actually learn some Cypher querying our graph here. Let's just start with a question that we might want to ask of the data, and we'll go through and build up a query that answers this question. So let's say that I want to find a brewery to go to. So I enjoy going to breweries. This is a common question at my house, is which brewery are we going to go to? So I want to find breweries near me that my friends also like, that have the highest rating. So let's think about this question and jump over to Neo4j. So here's Neo4j browser. I'm running Neo4j locally. If you haven't seen Neo4j browser before, there are a few nice features here. One is we can click this database slide out that will show us what node labels and relationship types and property keys we're working with. We can also have our saved queries here. We also have great access to the documentation. I'm not signed in to Neo4j Browser Sync, but with Neo4j Browser Sync, we can sync our saved queries and some other data so that the next time we access Neo4j, maybe on a different machine, we still have access to all of those. And of course, there are some configuration options for changing the theme, changing our graph visualization, things like that. And we can click on any of these node labels to just execute a simple query. So this, when we click on one of these, we simply say, well, find 25 businesses and return those, and we get this graph visualization. We can double click on any of these to expand out. So here we have the Holiday Inn Express. We can now see in blue the reviews for this Holiday Inn Express. So here's a review. It's a 5-star review. We can read the text of the review. It says outstanding staff, well-equipped rooms. Let me make this a little bigger so it's easier to read here. There we go. And we can explore the graph visually by sort of expanding nodes. So here's the user who wrote this review. We can see all of the reviews that this user wrote. He's friends with Jack. Jack has many more friends, wrote some reviews as well. So we can explore the graph that way. Or we can also write Cypher queries. So let's just match on all business nodes, and let's just return the count of all of those. So note here that in the match statement, which we said match statement is somewhat similar to a select in SQL. It takes a graph pattern, the pattern that we're trying to find. In this case, we want to find nodes with the label business. And when we find those, we're going to bind those to this alias or this variable b here, which we can then refer to later on in our query. So instead of returning all of the businesses, I'm going to return the result of an aggregation function called count, which will tell me the number of businesses that exist in the graph. And I have 144,000. So you can see in the browser, if we don't return graph data, we don't have a graph visualization. Previously, we were returning nodes. In this case, we're returning just a single scalar value. So we just have a tabular representation of the data. The other thing that's nice about Neo4j browser are these browser guides. So I wrote just a simple browser guide that we're going to work through in a moment here, just to provide sort of some structure for writing the query to answer this question. But there are lots of other browser guides out there. For example, the Graph of Thrones guide. This walks us through importing data from analyzing the text of the Game of Thrones books to find character interactions to show us things like who are the most influential characters. We can do clustering on these characters and so on, all in Neo4j. So that's really interesting. So that's the guide functionality. These are just HTML files that we can pull in to Neo4j browser. They can embed queries and text. So anyway, I wrote just a simple one here that we're going to use to give us sort of a skeleton to answer this question of what breweries near me that my friends also like have the highest ratings. So what we're going to do is we're going to break this down into a few different smaller parts, build up our more complex query to answer this. So the first thing we're going to do is start by finding all of the breweries. But before we do that, it's helpful to take a look at the data model. We can use this call statement, so call db.schema. db.schema is a procedure that, oops, spelled that wrong, db.schema, that will return a graph of the data model that we have loaded in Neo4j. So we said we have businesses that are in a category. We have reviews, or a user wrote a review, and that review reviews a business. And we have users that are friends with other users. So we want to remember this data model as we go through to construct our query. So the first thing we want to do is find all of the breweries. Well, hopefully there's going to be a brewery category. We said category is a node. So let's see if we can find the brewery category. So let's match on category nodes. And now we need some sort of filter, right? Because we can return C here. C is the category node that we're matching on in this graph pattern. But we don't want to return all of them. We only want to return categories where the name property, in this case, is equal to breweries. So the where clause allows us to define predicates that sort of filter our results. So in this case, we want to match on all categories where the name property is equal to breweries. And we can see we have one node here. We can double click to traverse out to see all of the breweries. We can traverse out to find the reviews of these breweries and so on. But we don't want to explore this visually to answer our question. We want to build up our Cypher query. So let's move on. Now that we know how to find the breweries category, we want to find businesses within the breweries category. We want to find the actual business nodes. So let's expand our graph pattern in the match statement to find business nodes that have a in-category relationship to category, where the name property of that category contains breweries. And let's return the brewery nodes this time, which I've called brew. So we return those, and we can see all of our brewery nodes here. So we found 368 breweries. That's good, getting closer. Now the next piece of this is find breweries near me. Now we could actually look at our latitude and longitude, since we have that stored as a property on each business, and we can use some of the spatial functionality to find breweries within a certain radius of our current location. But for now, I'm just going to search for breweries in the same city. Let's just say that I live in Phoenix. I don't actually, but fortunately we don't have San Mateo data in this Yelp example. So let's say I'm looking for breweries in Phoenix. So we can just extend our where clause here with an additional predicate to filter for breweries where the city property is Phoenix. Now we're down to 20. We've identified the 20 breweries in Phoenix. And the next part is a bit more tricky. We need to find breweries near me that my friends also like. So the first thing we need to do is be able to find me, so find myself in the graph. Now I'm not in here because I haven't reviewed anything in Phoenix, but I did just pick another user. We'll pretend this user is me. He's reviewed some things in Phoenix. He has some friends in Phoenix, so this should work out okay. So we can look nodes up by by, in this case, the value of user ID property. So I went ahead and grabbed that. So we can find this user here, in this case, Floyd. So we're going to pretend that I'm Floyd. So thanks, Floyd. But we need to find my friends. And then we also need to figure out how to define a like. So we're going to end up creating a bit more complex pattern here. So we have Breweries in Phoenix. Now let's add another match statement here. So the result, let's just say the paths that match a given graph pattern in a match clause are then passed through to the rest of the query. So in line 4 here, for this match statement, we're going to be taking all of the paths that we've found from the previous match and just working with those. So let's match on breweries that my friends like. How are we going to define a like? Well, let's look at reviews. So we'll match on reviews of these breweries. So brew here is an alias for all breweries in Phoenix that we matched on lines 1 through 3. We're going to find all the reviews written for those that were written by my friends. But how do I define a friend? How do I find those? Well, a friend is going to be any user that has a friends relationship to me. So I just need to match on user node where the user ID is equal to my user ID. So we've expressed a fairly complex graph pattern on line 4 here. We've said for all of our breweries in Phoenix, find all of their reviews, find who wrote those reviews, but only where those users have a friends relationship to me. So this is going to find all of the users who have written reviews that are my friends for breweries in Phoenix, but they may have written terrible reviews, and we don't want to go to any of those. So we'll add another filter here to filter where, let's say, the stars property is greater than 4. So only filter on breweries that have a very, very high review from one of my friends. Let's go ahead and run this. And now we're down to 13 breweries. We're getting closer. And the final piece of this is to find breweries near me that my friends also like with the highest rating. So I found 13 breweries that my friends also like in Phoenix that are near me, but I need to order those by rating because I unfortunately can't go to all 13 in one night. So in our return clause, let's return the brewery name, their address, and average of their rating. Let's order by average stars in descending order. Now there's a small problem with this, but let's go ahead and run this and see what we get here. And we can see that all of the average stars is 5. Well, why is that? Well, if we look at what we're taking the average of here, by the way, average is another aggregation function, and we said that when we return an aggregation function result along with anything else, we have implicit group bys. So in this case, even though we've built up all of these paths for my friends and their reviews, when we return an aggregation function result, we're grouping just by the brewery here. That's why we're getting one line per brewery with the average number of stars. But what we're taking the average of are just the reviews that my friends wrote here. And we have this filter so those stars are going to be 5s because the only thing greater than 4 in this 1 to 5 star system is a 5. So that's why our average is a 5 here. So instead, we need now an additional match to now match on all reviews. Let's call this R2. All reviews of these breweries, not just the ones that my friends wrote. Let's take the average now of the stars property on R2, which will be all reviews for each brewery. And now when we run this, we can see that we have some actual helpful results here. So we can see Rinhouse Brewing is top rated with 4.63 average, Helio Basin Brewing with 4.62, and so on. Switch back to the slides here. So this is the answer to our question. What breweries near me that my friends also like have the highest rating? We used Cypher to define some graph patterns to traverse the graph to answer this question. Hopefully we learned a little bit of Cypher along the way. Let's take a look at some components of Cypher that we used to answer this question. Well, we started off with a match clause, and match takes a graph pattern. So we saw how we can express simple graph patterns. And again, we saw previously there are more complex things we can do, things like variable length paths, those kinds of things. But we saw how we can express basic graph patterns. We saw how we can express some predicates to filter our results. We saw how we can use aggregations, things like the average and the count function, and we saw how to order our results. So a lot of these things, if you're familiar with SQL, should be pretty familiar. Things like ordering in descending order, things like average functions, those are pretty common to all query languages. But you'll also see things that are not common to query languages, like SQL, which is this idea of expressing a graph pattern. And finally, we saw that the answer to our question is not always graph data. It's not always a graph visualization. Sometimes it is tabular data, or a table of businesses and their average reviews. But note that in order to get that data, we did traverse the graph using this fairly complex graph traversal that we wrote to find breweries that my friends also like. So in the time that we have left here, I'll take just a couple of minutes to talk about some other things that we don't have time to look at in more detail, but that I think are really important with Cypher. The first is this idea of profile or explain. So this is a keyword that we can add to any Cypher query to see the query execution plan. So we said that Cypher is declarative, which means that we don't have to specify all of the database operations that we want to execute to complete our query. Instead, the Cypher Query Planner comes up with those, and it's very smart. It's able to take into account the state of the database to come up with a optimized query plan. Now, we can use Profile and Explain to visualize the query plan. Here's what our brewery query plan looks like. We can see we start with a unique index seek, then we do an expand, that's a traversal, then we filter based on something in our where clause. And profiling is very useful for performance tuning. If we need to improve the performance of a Cypher query, the first thing we often do is take a look at this query execution plan. We want to make sure that we're using indexes where we should be and not doing expensive operations, things like getting to the lowest cardinality first, things like this. There's a chapter in the Neo4j developer manual that has a little bit of information about query tuning. So if you're interested in that, I would encourage you to take a look at that chapter. We can also create indexes in Neo4j. We didn't talk much about this, but I think it's important to understand how indexes are used in a graph database versus how they're used in a relational database. In a graph database, we use indexes not to traverse the graph, but rather just to find the starting point for our query. So we were looking up me by user ID. We had my user ID, and we needed to look that up in the graph. We use an index to find that starting point, but then we traverse out without using index lookups with a constant time query performance. In a relational database, when we do joins, which is similar to a traversal, when we do joins, those are index-based operations because we're comparing where two sets overlap using an index. And the performance of those joins, that index operation, is dependent on the size of the data. So we see that performance start to break down when we're working with very, very large tables. I mentioned this briefly. We can also use some of the spatial functionality that's built into Cypher to search for businesses near us using latitude and longitude and a distance function. We can also extend Cypher with user-defined procedures and functions. So this is code that's deployed to the database, but that is then callable from Cypher. There are a few examples of this. So anyone can write a procedure and function and deploy it to Neo4j, but there are a number of libraries that exist out there that contain some common operations that are very helpful for working with graphs in Neo4j. There's the APOC library, which stands for Awesome Procedures on Cypher, that contains procedures and functions for things like data import from additional sources, things like importing from relational databases, things like working with parsing dates, graph algorithms, periodic jobs. There's a lot of things in APOC, sort of the batteries included piece of Neo4j. There's also a set of spatial procedures that expose things like creating spatial indexes, searching these spatial indexes using procedures. And there's also a GraphQL integration for Neo4j that translates GraphQL to Cypher and allows you to serve a GraphQL endpoint from Neo4j. So Neo4j is very extensible, and the mechanism that we use to extend Neo4j is through this user-defined procedure and function interface. Here's an example. In this case, I ran PageRank over this graph to find my most influential friends. So in the first line there, I'm just finding all of my friends. Then I collect them into a list. Then I call this PageRank procedure to run 20 iterations over my friends graph to find those that have the highest PageRank score. And this might be useful for finding influencers in a network or a social network analysis type queries. So let me just mention a few resources that might be helpful as you want to learn more about Cypher and Neo4j. The first is the Cypher ref card. This is a reference documentation for working with Cypher. It's very helpful. I use it pretty much every day when I'm writing Cypher queries. So I would really recommend to have this open. It has examples of the syntax for pretty much every Cypher operator and function. The next resource I want to mention is opencypher.org. This is the landing page for the OpenCypher project. As I said, OpenCypher, its goal is to provide the tools and materials necessary for people that want to implement Cypher on other systems. Cypher is not specific to Neo4j. It's really a graph standard, and there are other tools and databases that have adopted Cypher, things like SAP HANA, Redis Graph, and so on. There are a number of implementers group meetings if you'd like to have input into the process of formalizing the Cypher standard. You can join that group as well. Another good resource is the developer page. From here you can find code snippets and examples, as well as links to online and in-person training. There's a great 60-minute introduction to Cypher training that gives you a bit more hands-on work with learning Cypher. So that's a great resource to explore. And we mentioned this briefly. Neo4j Sandbox is a collection of on-demand Neo4j instances that anyone can spin up that include pre-built datasets and queries with these Neo4j browser guides that we looked at a minute ago that can show you how to write Cypher for specific use cases, things like building personalized recommendation systems or exploring IT and network management data, working with public data, things like that. So Neo4j Sandbox is a really helpful resource for exploring some of that data. Great. Well, that's all that I have for today, and I think we have some time to take a few questions. So let's go ahead and do that.
Awesome. Thanks so much, Will, for that presentation. And thank you, everyone, for joining us today and for submitting so many great questions. We only have time to take a few, but we'll take as many as possible. So, Will,
Yes, Corey.
the first question is kind of a long one. So here you go. It says, in your example, the stars rating is saved as a property of a node. Why is this preferable to creating 5 stars, 4 stars, etc. nodes and creating a relationship to those ratings? Would this prevent the use of functions like average and sum as you use them, or would this also be possible using the ratings as nodes? Are there general rules when to store data as a node and when to use it as an attribute, etc.?
Yeah, that's a great question that gets at sort of the iterative process of graph data modeling. So the first part of your question was specific to the review. So here, the blue node here is a specific review that was written by Sean of some restaurant called Modern on Melrose. And we've stored stars as a property on the review node. And I believe the question is, why do we store that as a property and not just create a node that's 1, another node that's 2, another that's 3, 4, and 5, and so on? Well, if we did that, then every 5-star review would have a relationship to the 5 node. And that's not necessarily a great graph representation. It means that it's a bit more difficult for us to do things like aggregating on the stars property of a review for a specific business. We can just use the average mathematical function to do that execution. We typically don't want to have nodes that are connected to a very, very large part of our graph. That's typically not a good thing that we want to see in graph data modeling. Now, your other question was more generally, what are some of the best practices for graph data modeling? There are a few of these. There's a great developer page. So if you go to neo4j.com/developer/ I think it's getting started, there's a series of developer guides. Here we go. We can just click on developer guides. And there's a section on working with data here that talks a little bit about graph data modeling and some examples. And I think oftentimes we talked earlier about when should something be a node versus a property. The example I gave was the category of a business. So why did we model category? So here we have hairstylist. Why do we model this as a node and not as a property on a node? Well, if we're doing some sort of similarity or recommendation query, we might want to be able to traverse through this node to find other businesses that share the same category. And that's easy to do if we just have one, but what if we want to find businesses that are hairstylists that are maybe also I don't know, budget hairstylist, something like that across more than just one category. We can do that by traversing through it. So in terms of should something be a node or a property, I like to ask the question of, can I discover something useful by traversing through this if it's a node? And if the answer is yes, then I model as a node, not a property.
All right, awesome. We'll take just one more question since we're running out of time, but we'll do our best to get back to you all with answers. Last question. Do lots of indexes start slowing down the database? What's the best practice regarding that?
Yeah, that's a good question. So currently, Neo4j, like a lot of other database tools, uses Lucene under the hood for indexing. And your question is, does creating lots of indexes slow down the database? And if we have lots and lots of indexes, we may start to see some write performance degradation because we need to update all of these indexes in the context of a transaction to keep those updated, since Neo4j is a transactional database. So if we have lots and lots of indexes, we may see some write performance degradation. And it's important to remember, though, how we use indexes in a graph database. We only use them to find the starting point for a traversal. So oftentimes we find that we only need just a few indexes for our data, because there are only a few different properties that we want to do a lookup for to start our traversal. So in this data set, an example is user ID, maybe business ID. Maybe we want to create an index on the text property of a review because we want to find reviews that contain certain keywords, um, but there aren't really that many more indexes that we want to create. So if you find yourself creating lots and lots of indexes, I think you want to ask the question, am I actually using this index to find the starting point for a traversal? And if the answer is no, then you don't need it.